Welcome to Accelerated Math 108, Module 11.4. In this lecture video, we're going to take a look at how we can use a system of linear equation to solve distance, rate, and time problems. All right. So these problems are very similar to the ones that are in Module 9. So as far as distance, rate, and time problem, they are based on scenarios. Okay. So the scenarios tells us how to write out these equations. So some of these problems I'm going to show you in this particular module 11.4. Some of them we can use one variable to solve. We can set it up as one variable. Some problem we have to set up as two different variables. So I will try to do both from time to time. So let's take a look at this first one. Oh, as you can recall, when we're dealing with distance, rate, and time type of problem, distance is always equal to rate times the time. All right, so we will either translate for the rate or we will translate for the time. So every one of these problems got something to do with the distance. So I'm using the distance to help me write out the equation. We just have to be able to translate for the rate or the time. So this first problem, two buses leave Chicago at the same time, traveling in opposite directions. So this particular example is traveling opposite direction or traveling away from each other. So I'm going to put it up here. Travel away from each other. One bus travel 54 miles per hour, the other travel at 63 miles per hour. So how soon will they be 234 miles apart? So let's say Chicago is right here. They're traveling opposite directions. So one bus goes this way, the other bus goes that way. All right, so let's say my one bus is going at 54 miles per hour. The other bus is going at 63 miles per hour. So the question is, what is the time they will be 234 miles apart? So what the 234 mile means is after some time, both buses leave at the same time and travel so long, then let's pretend they stop after so long, then the distance that both buses traveled is going to be that 234 miles. All right, so we know the bus that goes faster will travel more distance. The bus that goes slower will travel lesser distance. But after both buses travel some time, when they stop, then they will be 234 miles apart. So the distance of that one bus going to the right plus the distance of the other bus going to the left is going to equal to 234 miles. All right, so our job is to find the time. Okay, how soon would they be that many miles apart? So let's see, I got one bus and I got the other bus. The problem already told me the rate for one bus is 54, the other bus is 63. So what about their time? Well, if you think about it though, one travel one way, one travel the other way. So since they left at the same time, after so many hours, they will be 234 miles apart. So that means both of them actually travel the same amount of time. So if I use two different variables, I will say call one of them to be X for that one bus. We can say the time for the other bus will be the Y. So since I'm dealing with two different variables, there got to be two things I need to write out my equation. So one of them is regarding to the distance. The other one will be the time. All right, because both of them will travel the same amount of time and stop to equal up to 234 miles apart. So the time for that one bus got to equal to the time of the other bus. All right, so these are the two things I needed to write out my equation. So let me go ahead and put the time as the first one. So we say time for one bus is x, which is equal to the time of the other bus. Now let's do the distance as the second equation. Distance of one bus. Distance is always equal to rate times time. So that will be 54 times x plus the distance of the other bus, which is rate times time, 63 times y, 63y, equal to the total distance away, 234 miles apart. So that's how we set it up using two variables. Now, if I want to set up this problem using one variable, then all I needed is the distance formula. Because if I only use one variable, well, not the distance formula, all I needed is the concept of the distance. If I'm using one variable, that means by knowing the time are the same, that means the other bus, you know what, let me rewrite it. That means the other bus will have the same time as that one bus. So let's call both of them x. So let me show you why one variable makes sense. Because the distance of one bus, which is 54x, plus the distance of the other bus, 63 times x, is equal to 234. All right, so that's how we will write out the equation using one variable. Now, what's the difference between the two techniques? They're actually the same. Because if I want to substitute x for y, all right, every x I see, I will substitute for a y. Or, tell you what, let's do it the other way. I'm going to substitute for y. So that means for every y, I'm going to substitute for an x. So if I substitute x for the y, that will be 54x plus 63 times x equal to 234. You see the two equation, either I use one variable or two variable, the two equations are exactly the same because we can only solve one variable at a time. So these two are exactly the same equation. All right, so let's continue to solve it. Let's combine some like terms. 54 plus 63, 117x. Set it equal to 234. Divide both sides by 117. My answer, 2 hours. So that means after each one driving 2 hours, okay, or both of them on the road 2 hours, 2 hours later, they will be 234 miles apart. So since the time's got to be the same, my answer would just be 2 hours. All right. So traveling away from each other. That's the example for this scenario. All right, let's take a look at another example. This won't let me move. Two trains leave Cleveland at the same time. All right, they're leaving at the same time. One travel east and the other travel west. So this one is very similar to traveling away from each other because one go to the right, one go to the left. The speed of the westbound train is 4 miles per hour greater than the speed of the eastbound train. So this sentence is the one I got to translate. The westbound is 4 more than the speed of the eastbound train. And they're talking about speed, so I got to translate for the rate. All right, so let's see. I got eastbound train and I got westbound train. I got rate, I got time. So who gotta be x? Comparing between two items, the one listed at the end of the sentence is x. So the eastbound train gotta be x. The westbound train will just be 4 plus x because greater than means plus. after 3 hours, they are 696 miles apart. So that means eastbound train go to the right 3 hours, westbound train go to the left 3 hours. So both of them travel 3 hours, so they travel the same amount of time. Then they stop. They will be 696 miles apart. So the east and the west, okay, traveling away from each other. So after 3 hours, the total distance between them is this 696. All right, so as you can see, I'm only using one variable in this case. So I'm going to do it right here, okay? So the distance of the eastbound train plus the distance of the westbound train got to equal to 696. Distance equal to rate times time, so x times 3 is 3x, plus the distance for the westbound train, time is 3 times the rate, 4 plus x, together equal to 696. All right, that's using one variables. Now, if I want to use two different variables, let's take a look. Two variables, I still need my distance concept. Now, my second equation or another equation got to be about this translation. So let's say eastbound train, westbound train, okay? So I got speed and I got time. I know the time is 3 hours, okay? So I don't know about their speed. So let's say the eastbound train is x, westbound train is y. My first equation got to be regarding to the translation here. Westbound train is, so this is about speed, right? So the speed of the westbound train, that's y. Is means equal 4, I write 4. Greater than, I write plus. Plus who? Plus the speed of the eastbound train, which is, I call it a x. All right. Why it is not y plus 4 equal to x? Well, because like we mentioned in other module before, the westbound train is faster than the eastbound train. So if the west is already bigger than the eastbound train, then if I want to make them equal, I cannot say westbound train plus 4 because the westbound train is already faster. So that means for the two to be equal, for Mr. Chen and Donald Trump to be equal, then we got to plus the 4 on the smaller amount in order to equal to the larger amount. Okay, that's why these type of translation makes sense when I use two variables. All right, which is a little bit different than using one variable to translate. All right, so now the second equation got to be regarding to this distance, so that's the same thing. That will be distance of the eastbound train is 3x plus the distance of westbound train is 3 times the rate, 3y, together equal to 696. So now my first equation is already saying y equal, so I can substitute 4 plus x into the second equation wherever I see on y. So once I do that, that will be 3x plus 3 times parenthesis 4 plus x equal to 696. You see, the two equations are exactly the same. So this particular example, I can also use one variable. So let's see, let's solve for x, okay? The question wants me to find the rate of each train. So I'm just going to go back to the one variable. All right, distribute right here. Then I get 3x plus 12 equal to 3 plus 3x equal to 696. That will be 6x equals. Let's move the positive 12 over. That becomes subtraction. 696 minus 12. 684. Divide both sides by 6. My answer, the speed of the eastbound train, 114. All right, so that's for the eastbound train. All right, remember now the westbound train is 4 mile per hour greater, so that would just be 4 plus 114. So that would make the westbound train 118 to be the westbound train. All right. So same equation. Either I use one variable or use two different variables for this problem. All right, this scenario here is traveling towards each other. Two planes leave from points that are 1650 miles apart at the same time, traveling towards one another, flying at a different altitude, of course. So this is what I call travel towards each other. So what the 1650 means is one of them is on one plane on one side, one plane on the other side. That's called the plane 1 and plane 2. They are traveling towards one another. Okay, 1650 miles apart. So that tells me the distance was already 1650 miles apart. If the rates are 285 and 375 mile per hour. So let's say one airplane goes 285, the other one goes 375. So I know the one traveling faster will cover more distance than the one traveling less. How soon will they meet? So basically, by the time they made up, since they left at the same time, that means by the time they meet up, both of them has traveled the same time as well. Okay, just like the very first one I showed you. Okay, got to travel, they're leaving at the same time, so by the time they made up, or by the time they are so many miles apart, both of them has traveled the same amount of time. So if I know the time are the same, all right, I'm just going to use one variable for this one. So I'm going to call it the plane number 1 and plane number 2. All right, I got rate, I got time. I need to translate. We're saying the time is already the same, so let's call them x. So the plane, the first plane, let's say it is 285 miles. The other one is 375. How soon will they meet? So I'm looking for the time they will meet, which they both of them won't fly the same amount of time once they meet. So the distance for plane number 1 will cover so many distance, plus the distance for plane number 2 will also cover so many distance from the other side. But once they meet, the two plane has covered a total of 1650. Okay, that's the idea. So again, rate times time to find the distance for each one. That's 285 times x plus 375 times x equal to 1650. All right, combine like terms. 285 plus 375, 660x. So that equal to 1650. Divide both sides by 660. 1650 divided by 660. 2.5. So how soon will they meet? How soon will they meet? 2.5 hours. Both of them will travel 2.5 hours in order to cover the 1650 miles. All right. So these three examples are very similar, traveling away and traveling towards each other. All right, let's check out another one. Steve and Dave live 666 miles apart. They start at the same time and travel toward each other. So this is the same problem as the previous one. Steve's speed is 3 miles per hour greater than Dave's. All right, so I got Steve and I got Dave. All right? Rate and time. So they're traveling towards one another. So at the very beginning, it already told me they are 666 miles apart. So let's say that's Dave. This is Steve. And Steve's speed is 3 miles per hour greater than David's. So if I use one variable, let's translate for this. Comparing between two items. So David lives at the end, so David will be X. David. Yeah. So David will be X. Let me write this a little bit nicer. All right, so Steve will be 3 miles per hour greater than means plus David's speed. If they meet in 6 hours, so Dave drives 6, travels 6 hours, Steve travels 6 hours, then they will meet. So when they meet, that means they have traveled 666 miles. So that means the distance that David traveled plus the distance of Steve traveled got to equal to 666. All right, so distance equal to rate times time. So that'll be 6 hours times 3 plus x in the parenthesis plus 6 times x, which is 6x equal to 666. All right. So if I want to use two different variables, then one equation got to be regarding to this distance the two traveled. The other equation got to be about the translation. So let's just say, I'm going to put this in blue, okay? Let's say, still call David to be x, okay? Let's call the Steve's speed is y. So Steve, y is means equal. 3, 3. Greater than means plus. Plus who? David's. Which is, we call it x. So that's the first equation. All right, second equation got to be about the distance. So distance for David will be 6 times x plus the distance that Steve covered, rate times time, which is 6y, equal to 666. So if I do a substitution, take my y equal 3 plus x and substitute into the second equation for y, right? Y equals, so I substitute for y. If I put that right here, okay? If I put it right there, that would just be 6x plus 6 times parenthesis, 3 plus x equal to 6. Okay. I'm sorry, maybe I wrote it down wrong. Let's do it this way. Let's just say, oh, Steve is y. Let's do Steve. Well, let's do David first. Never mind. Let's do the same thing. There you go. All right, so these two equations are exactly the same. All right, so using two variable or one variable for this problem doesn't make a difference. All right, let's do some distribution here. I'm going to go back to my one variable. All right, that would be 18 plus 6x equal to 666. Combine like terms. That would be 12x on the left side. All right, let's move my 18 to the other side, become negative. That will be 666 minus 18. That will be 648. Divide both sides by 12. My answer, x equals 54. And who represents x? The speed for David. So David is going to be 54 miles per hour. Steve is 3 miles per hour greater. That will be 3 plus 54, which is 57. Okay, that's all we do. All right, let's take a look at this one. Let's see what scenario this one fall into. Jim traveled 5 miles per hour less than 2 times as fast as Brenda. Okay, so I got Jim compared with Brenda. Jim, Brenda. All right, I got speed, I got time that I need to translate. So if I just translate for this very first phrase, two items. Brenda lives at the end, so Brenda got to be X. And this is talking about speed, right? So Jim is 5, I write 5. Less than is subtraction sign go in front. 2 times who? 2 times Brenda, which I say is X. Okay. Starting at the same point, traveling in the same direction. Okay, so Jim, Brenda. Starting at the same point, traveling in the same direction. Let's just say they're all going to the right. They are 292.5 miles apart after 7.5 hours. So what does that mean? Let's see. Jim traveled 5 times less and 2 times as fast as Brenda. So somebody got to go faster than the other. It doesn't matter who goes faster here. What it's saying here is if they go in the same direction, starting at the same place, after 7.5 hours, they are 292 miles apart. So what that means is the one that travels faster, which will cover more distance. All right. So when they say they are 292 miles apart, that's referring to the difference between them. At exactly 7.5 hours, they are 292.5 miles apart. So that's referring to the difference of their distance because one of them got to travel faster than the other. So the difference is this 292. So what does that mean? That means the distance for one, the distance for Jim minus the distance that Brenda traveled got to be the 292. Okay, going the same direction from the same starting point. After so long, they are so many miles apart because one traveled faster than the other. So that many miles apart got to be the difference between them. Now, how do I know Jim travels faster? Well, because Jim is already twice as fast as what? Brenda. So naturally, Jim goes faster, which cover more distance. So that's why I got to put the distance for Jim at the beginning. So the time is 7.5 for both. So I'm just going to use one variable in this case. All right. So this scenario is traveling in the same direction. Same direction. All right. Distance for Jim, rate times time, that will be 7.5 times 2x minus 5, minus the distance for Brenda, rate times time, x times 7.5, 7.5x. The difference between them is 292.5. All right, let's do a quick distribution. 7.5 times 2x, which is 15x. 7.5 times 5, 37.5. Negative 37.5 minus 7.5x, 292.5. Combine like terms. 15 minus 7.5 is again 7.5. X, move the negative 37.5 to the other side, become positive. That'll be 292.5 plus 37.5. That'll give me 330. Divide both sides by 7.5. My answer. Okay, 44. So the speed X representing Brenda. So Brenda is traveling at 44 mile per hour. Jim is twice, 2 times the 44 minus the 5. So Jim travels 83 mile per hour. Okay, there you go. So if you want to set up for two equations using two different variables, we still need this distance formula. That's one equation. The other one would just be the translation part. So if I say Brenda is X, Jim is Y, then that would say Y equals 2X minus 5. Okay. So that's how we would do it. Then we can use the substitution methods and still have the same equation right here. All right, traveling in the same direction, leaving at the same, starting from the same point. All right, let's take a look at this one. Two planes just took off from Reno. The first plane traveled 2 times as fast as the second plane. So I got 2 planes. The first plane and the second plane. After traveling the same direction for 8 hours, so this is the same type of problem as the previous one. They are 808 miles apart. So if I will translate this phrase, the first plane traveled 2 times as fast as the second one. So second one is X. The first one is twice as fast, which is 2X. So that's my speed. After both of them flying for 8 hours, the distance between them is 808 miles apart. So that means the distance of the first plane, which will cover more distance, right, because it's flying faster, minus the distance of the second plane, got to equal to the 808 miles apart, which is just like the previous example. All right, so if I do a rate times time, that would be 16x minus rate times time, ax equal to 808. That's 8x equal to 808. Divide both sides by 8, that will be 101. That means the second airplane is flying at 101 miles per hour. The first one is twice as that, which is 202. All right, that will be the answer for the speed of both planes. All right. I am going to flip-flop these two problems real quick. I'm going to go over this one first. Kevin made a business trip of 312.5 miles. He averaged 60 miles per hour for the first part of the trip and 55 miles per hour for the second part of the trip. So this is the scenario where different speed at different part of a trip. Okay, because one part he drive faster, another part he travels slower. All right, so if the trip took 5.5 hours, how long did he travel at each rate? So let's say this is where Kevin starts. And he going. And then there is actually somewhere he reached. All right. Then this is actually the first part of the trip. So after this point, he's changing his speed. So this is the second part of a trip, and this is where the destination is. Okay, so we got different speed at different part of a trip. So let's say we have first part and second part. We got rate, we got time. The problem already told me the first part of the trip he was going at 60 miles per hour. Second part, he slowed it down. Maybe the popo will try, maybe there's too many state trooper on the road. Now, what about the time? the question want me to find what's the time, okay, for each part of the trip. So if I'm using one variable here, one of these got to be x. So let's just say second part is x. You know what? Let's just say first part is x. So it don't really matter. Somebody got to be x. If the first part of the trip he spent x number of hours, what would the second part be? And this is where in module 9 we're talking about you and I have a total of 5.5. If you have x, then the other one will get the total minus what you got, what the first person gets. Okay, it's the you and I concept. All right. Now, so let's just go ahead and set it up. So how do I write out the whole equation once I translate? Well, here is the whole entire business trip to 5.5 hours. So one is x, the other one is the total minus x. And the distance for the entire trip is at 312.5 miles. So basically the distance for the first part of the trip plus the distance of the second part of the trip got to equal to 312.5. So the distance for the first part, rate times time, which is 60x, plus the distance for the second part of the trip, rate times time, 55 times 5.5 minus x, equal to 312. Now, if I want to use two different variables to do this problem, let's keep the first part of the trip's time as x. The second part is called the y. So the entire trip, first part plus the second part, together is 5.5 hours. So that's one equation I need. So that will be x plus y equal to 5.5. Let's call that the first equation. The second equation got to be about this total distance. So the distance of the first part, rate times time, plus the distance for the second part of the trip, rate times time, 55y, equal to the 312.5. All right, let's call that the second equation. So let's do substitution methods. So let's solve for y in first equation. So to get y by itself, I gotta move my x over, so that will be y equals 5.5 minus x. Call this equation number 1 prime, because now I need to sub equation number 1 prime into the second equation. Wherever I see an x, so, whenever I see an y, so I'm gonna take my 5.5 minus x and substitute into the second equation wherever I see in y, which is right there. So that means my equation now will be 60x plus 55 times 5.5 minus x equal to 312.5. So this equation is the same as if I would use one variable. Okay. All right, let's go back to my one variable ones. It's the same thing. I'm going to do a distribution. So 60x, first term is still first term, 60x. 55 times 5.5. 302.5 minus 55x equal to 312.5. Combine like terms, 60 minus 55 is 5x equals. Let's move my positive 302 to the other side. That becomes subtract. So the 312.5 minus the 302.5. That gives me 10. So divide both sides by 5. My answer x equal 10 divided by 5 is 2. So that means the time for the first part of a trip is 2 hours. So the second part of the trip is 5.5 minus 2, which is 3.5 hours. There you go. Together is the 5.5 hour trip. So this scenario is about different parts, okay, different speed at different part of a trip. All right, this very last one, excuse me, I got to use two different equations. I got to use two different variables. It says a small plane flew 903 miles in 3.5 hours with the wind. Then on the return trip flying against the wind, it traveled only 588 miles in 3.5 hours. So why did it go less than miles? It went less than mile because flying against the wind means the speed of the plane goes slower. So in the same amount of time, it can only reach 588 miles. With the wind, speed is faster. Okay, so I cover more miles in the same amount of time. All right. So the question asks, what were the wind velocity and the speed of the plane? So let's see. Speed of the plane means how fast the plane could fly with no wind. All right, so I'm going to just say x is the speed of the plane. That's called the variable y, the speed of the wind. All right, so I got with the wind or against the wind. I got distance, I got rate, and I got time. So the distance for flying with the wind is 903. Against the wind is 588. All right, the speed. Well, let's do time first. The time for with the wind or against the wind is 3.5 hours. So what's the speed for the plane? Well, I got speed, I got planes, and I got wind speed. So normally you don't want to have the wind controls your plane because that means turbulence, okay, which is not good. So the speed of the plane always goes first. The speed of the wind goes second. Flying with the wind, like Gone with the Wind, speed is faster, so that will be plus. Against the wind, the airplane goes slower, so that will be subtraction. There you go. So this table is basically your equation. One right there, the other one right there. Distance equal. Distance equal rate times time. So that's 3.5 times x plus y. All right, distance equal rate times time. Rate times time, 3.5 times x minus y. There you go. All right, so now each equation only has two terms right now. So if I will divide both terms by 3.5, let's see if we get lucky, okay? 903 divided by 3.5. Yes, 258. Let's try this one. 588 divided by 3.5. Yes, got lucky, whole number. So my equation is 258 equals. So if I divide it by 3.5 on both sides, then the right-hand side will be a 1. And that 1 do a distribution to bring out your x and the y. So that's 258 equal to x plus y. And the other one is 168 equal to x minus y. All right, since my coefficients are already the same between the x or the y, I'm going to go ahead and do elimination. So I'm going to eliminate x. Or you can eliminate y, it doesn't matter. If I want to eliminate x, the coefficient, these two terms has exactly the same sign, so we will subtract. I'm going to take the top, subtract the bottom, okay? So 258 subtract the 168 is 90 equal 1 minus 1. The variable x cancels out. 1 subtracts negative 1 means 1 subtracts negative 1 means 2. So that will be 90 equal to 2y. Divide both sides by 2, y equal to 45. So that means the speed of the wind is 45. All right, so let's sub my y equal to 45 back into not the original first two. I can do the one I simplified. I'm going to pick the first one. I'm going to call this 1 prime, okay? Work down to 1 time. So that's 258 equal to x plus 45. I picked the first one here because I don't have to worry about this negative y thing. Move the 45 over, becomes subtraction. That will be 258 minus 45. The speed of the airplane is at 213 miles per hour. So that's the speed of the plane. All right. So, as far as distance, rate, and time problems, sometimes we can use one variable, sometimes we can use two variables. It really depends on the type. It really depends on the nature of the problem. And so we're looking at different types of scenarios as well, just like in Module 9. All right, that will conclude this lecture video. Thank you for watching.